A revolution is quietly underway on the Indian subcontinent, one that has the potential to redefine not just the character of India's future conflicts, but also the logic by which nations wage wars in the 21st century. In a technological partnership rarely seen in defense innovation, Chennai-based Zuppa and Navi Mumbai's Divide by Zero have converged to launch India's first 3D-printed mobile drone fabrication units. At first glance, the concept appears simple: deployable mobile factories capable of designing, building, and deploying custom drones at forward locations. But under the surface, this is a transformative leap in military science, drawing on advances in additive manufacturing, digital design, materials engineering, artificial intelligence, and autonomous robotics. The heart of this new capability lies in the flexibility and speed inherent in 3D printing technology. Unlike conventional drone production lines, which are tethered to fixed factories with rigid logistical supply chains, mobile fabrication units decentralize manufacturing, bringing it directly to the battlefield. Each unit packs high-throughput, multi-axis 3D printers capable of handling aerospace-grade composites, metals, and advanced polymers, along with embedded microelectronics print beds and AI-guided assembly robotics. This setup enables operators to upload a drone design, select mission-specific parameters, range, payload, endurance, signature, and produce fully functional, war-ready drones within hours instead of days or weeks. Such adaptability represents a watershed in the production of unmanned aerial vehicles. With modular printheads and a library of open-source and proprietary drone blueprints, Zuppa's system is designed to switch between fixed-wing reconnaissance types, multi-rotor kamikaze models, heavy-lift quadrotors for supply drops, or stealthy, radar-absorbing scout drones. The fabrication software incorporates generative design, an AI-driven process that iterates structures for weight, strength, aerodynamic profile, and signature management, yielding airframes optimized for specific mission envelopes and terrain. Onboard diagnostics continuously monitor layer fidelity, internal stresses, and chemical bonding of each print, ensuring aerospace-class reliability under field conditions. The synergy with Divide by Zero's 3D printing expertise elevates the technical frontier. Their proprietary, Acucraft, systems employ multi-material lamination, variable density infills, and integrated microchannel cooling, allowing combat drones to be made not only faster but also stronger and lighter using fewer raw materials. These printers can work with advanced filaments such as carbon fiber-reinforced nylon, Kevlar-based composites, or next-generation, radar-absorbent thermoplastics. The shift from slow, batch-based manufacturing to digital, on-demand printing means Indian forces can now iterate drone variants, adapt to enemy jamming or air defense, and recover quickly from attrition by scaling up custom fleets with minimal lead time. A pivotal benefit of mobile drone printing is the drastic reduction of logistical vulnerability. Traditional UAV programs depend on cumbersome supply lines, centralized warehousing, and slow-moving approval for design changes, a costly liability in fluid battlefields seen in Ukraine and Russia, where rear-area drone depots are frequent targets. Within field fabrication, India's armed forces can rapidly push replacement swarms, repair battle-damaged platforms, and upgrade payload suites on the fly, even in contested or communications-denied environments. Each mobile unit is network-aware. Drones, when recovered, can upload mission logs, sensor data, and damage diagnostics, feeding an AI-driven design loop that continuously refines airframes and avionics for evolving threats. Technologically, Zuppa's platform leverages automation and AI at every step. From preprint simulation that virtually flights tests airframes for aerodynamics, G-load endurance, and stealth coefficients, to post-print calibration where electronic warfare modules are tested for RF emission management, the mobile unit minimizes manual errors and maximizes mission adaptability. Swappable printer heads and tool modules are hot swappable, ensuring the system never needs to be shut down for reconfiguration. Built-in power systems, solar, battery, and mobile diesel gensets enable week-long autonomous operation in off-grid forward operating locations. Embedded in each freshly fabricated drone are modular avionics suites, open-source flight controllers, encrypted comms modules, smart GNSS receivers, and plug-and-play payload bays. A drone intended for surveillance might get a multiband EO/IR gimbal, mesh relay antennas, or SIGINT sensors. One intended for strike missions can be fitted with shape-charge warheads, ECM pods, or precision delivery mechanisms. This plug-and-play approach, combined with a microrobotic line operating under cleanroom class contamination control, streamlines the integration and testing process typically associated with centralized armament factories. 3D-printed drones can also employ advanced camouflage. Filaments can incorporate chameleon pigments or textures that match specific terrains, and counter-lidar microstructures enhance survivability against enemy counter-UAV batteries. Heat sinks and distributed electronics further minimize thermal signatures. In high-threat environments, the system can churn out expendable, one-way drones for saturation strikes, a tactic that has proved decisive in the Russia-Ukraine war, where drone swarms have overwhelmed advanced ground-based defenses not by individual sophistication, but by sheer numbers and continuous replacement. At doctrine level, this capability heralds a shift in Indian tactical and operational planning. War gaming at major defense colleges now factors in organic, on-demand drone production at brigade or division level. Every Army battle group, naval flotilla, or airbase can be provisioned with its own mobile factory, drastically shortening the OODA loop: observe, orient, decide, act. Indian planners see this as a hedge against the industrial warfare, repeat in Ukraine, where one side's drone depletion became critical in weeks, and the force able to regenerate unmanned wings on demand imposed heavy attrition on the slower, less agile adversary. Destructive kamikaze drones, or loitering munitions, produced onboard the Zuppa DBZ units using warhead inserts supplied from standard ordnance stockpiles, give India an asymmetric advantage to strike deep, fluid enemy rear areas with minimal reconnaissance to strike delay. In an Indo-Pakistan or India-China conflict, facing dense sand belts and anti-access zones, mobile units continuously refine aerodynamic or electronic countermeasure print parameters, iterating with every adversary engagement. The doctrinal flexibility to print payload-optimized drones, whether for anti-radiation, yield decoy, or armor-penetrating missions, renders Indian unmanned forces nearly inexhaustible within the operational theater. Strategically, the Zuppa DBZ technology closes the loop between homegrown AI, materials research, robotics, and military application. The field unit's print queues recognize component scarcity and reoptimize blueprints for what's available. In a blockade scenario or heavy jamming, the drone factory can shift materials mix and print substitution protocols, keeping drone throughput high despite denied access to global supply chains. The visibility learned from Ukraine, where commercial drones and 3D-printed spares tip the scales in city sieges, translates into doctrine that values not only quality but rapid, adaptive manufacturability. Critical, often overlooked scientific feat lies in the way these units manage quality assurance and failure prediction. Embedded sensors in the printers monitor temperature gradients, component stress risers, and microcracks, uploading data to onboard neural networks that flag flawed parts before assembly. This statistical process control, inspired by aerospace manufacturing, ensures that even on rough terrain or in harsh climates, airframes meet rigid fatigue and tolerance margins. Some fabrication units may even print repair kits, snap-on braces, landing gear, or control surface panels, allowing field operators to restore damaged drones without ever returning to a main base. In a truly future-oriented twist, the drone blueprints themselves are updatable in the field. New algorithms for countermeasure evasion, power management, or autonomous targeting can be downloaded over secure mesh networks or even sideloaded directly from accompanying command vehicles. This means as Indian or allied intelligence identifies new electronic threats or mission profiles, the entire drone swarming capability can be recalibrated in near real time, at the edge of battle. At its most consequential, the mobile drone factory concept acts as a national force multiplier. Zuppa's and divide by zeros approach democratizes advanced aerospace production, making every forward base not only a launch site but a tech incubation center. This has profound implications for India's broader defense industrial ecosystem. Local adaptivity and resilience combine to immunize the war effort against strategic bombardment or cyberattack on central nodes. The net effect is an armed force that can not only weather severe attrition but remain tactically nimble, operationally unpredictable, and logistically autonomous for extended campaigns. For the scientific community, the ripple effect is clear. Each 3D printing campaign generates new data on component stresses, mission impacts, and failure signatures, Every recovered drone sends telemetry for further optimization. This feedback-over-fit cycle supports a virtuous loop in Indian drone research, fueling innovation in AI, software, exotic printing, and G materials and battlefield robotics, where Ukraine and Russia have shown the world that the side better able to field, replenish, and adapt drone forces often dictates tactical momentum. India's 3D-printed mobile drone manufacturing leapfrogs both, envisioning a future where unmanned air power is locally produced, endlessly adaptable, and always available, regardless of the fortunes of war. In such scenarios, numbers, iteration speed, and digital adaptability are as decisive as traditional metrics like jet count or missile inventory. For adversaries, the calculus is daunting. With every new Zuppa DBZ module deployed, the prospect of denying Indian units unmanned reconnaissance, strike, and yield capabilities becomes virtually impossible. As battlefield AI, multispectral sensors, mesh networking, and adaptive materials converge, the result is a doctrine of manufactured omission. The right drone in the right numbers for the right task every time. Thus, India, by embracing the synthesis of rapid manufacturing, modular design, artificial intelligence, and digital logistics, secures more than just an edge in drone warfare. It pioneers a flexible, scalable approach to future conflicts, becoming not just a consumer of cutting-edge military technology, but a global standard-bearer for warfighting innovation in the digital, drone-dominated age. History is rich with lessons showing how revolutionary technologies have upended established doctrines, rewired military thinking, and swung the fate of nations. The partnership between Zuppa and Divide by Zero and their fieldable mobile drone production units stands in a long lineage of technologies that have redefined the meaning of battlefield advantage. At the dawn of the 20th century, the introduction of the machine gun changed warfare almost overnight. No longer could massed infantry attacks carry the day, as they had in the age of Napoleon. The relentless, mechanized firepower of guns like the Maxim rendered old tactics obsolete. The trench warfare of World War I was both a symptom and a consequence of this disruptive innovation. The arrival of the tank, first seen at the Battle of the Somme and later refined on the fields of Cambrai and Amiens, similarly reshaped strategic calculus. Mobile, protected firepower untethered armies from defensive lines and reintroduced maneuver in war on an unprecedented scale. Armies that recognized and rapidly integrated mechanized forces, most notably Germany's Blitzkrieg approach in World War II, achieved swift victories and fundamentally rearranged frontline dynamics. The emergence of military aviation, beginning with reconnaissance planes above the Western Front and culminating in strategic bombers, fighters, and carrier-borne aircraft, brought a vertical dimension that shattered ancient limitations on speed, reach, and surprise. Pearl Harbor's devastation was wrought by air power. The Doolittle raid and countless subsequent campaigns demonstrated that whoever mastered the skies could dictate terms on the ground and at sea. Radar, first used in the Battle of Britain, gave defenders real-time insight into enemy approach vectors, fundamentally altering air defense. The side with superior sensing won the battle before the clash began, as fighters vectored with precision to intercept and destroy the bombers that once terrorized cities unchecked. The revolution continued with nuclear weapons, whose strategic impact went far beyond the immediate devastation of Hiroshima and Nagasaki. The mere possession of such technology rewrote deterrence, diplomacy, and the long peace, ushering in an era where conventional force often served only as a veil behind which nuclear posturing decided the outcomes of crises. In the late 20th century, precision-guided munitions gave birth to a new approach: smart warfare. In Operation Desert Storm, the U.S. military's deployment of GPS-guided bombs, stealth aircraft, and tactical networking made swift victory possible against a numerically superior Iraqi opposition. The lesson was clear: quality, connectivity, and rapid adaptation could outweigh mass. The information age followed. The introduction of battlefield GPS, digital communication systems, Blue Force trackers, and real-time UAV feeds transformed the fog of war. Combatants who could assemble, analyze, and act on battlefield data in minutes, not hours, gained not just tactical but operational and strategic superiority. In Kosovo and later Iraq, digitally networked forces exploited speed and awareness to dismantle enemy resistance and achieve objectives with unprecedented efficiency. Most recently, the drone revolution has unfolded before our eyes in the Russian-Ukrainian conflict. Ukrainian forces, sometimes outnumbered and outgunned, have leveraged swarms of commercial and custom drones for artillery spotting, reconnaissance, strike missions, and electronic warfare. The ability to rapidly adapt drone platforms, employed in large numbers, has neutralized advantages in armor and artillery. Russian forces too have discovered the power and peril of unmanned adaptability, as both sides race to iterate new variations, evade countermeasures, and replace losses in near real time. Observers agree. The ability to manufacture, modify, and deploy drones faster than the enemy has become the coin of modern battlefield survival and success. In all these historic pivots, from the Maxim gun to the tank, from aviation to radar, from nuclear postures to precision-guided and digital war, the recurring theme is speed of adaptation and decentralized, scalable technology. Armies that embrace new tools, integrate them into doctrine, and push production to the edge gain more than mere advantage. They seize the course of events and force adversaries into reactive, defensive postures. Zuppa and Divide by Zero's mobile 3D drone factories echo the legacy of these predecessors, bringing manufacturing and innovation directly to the frontline, democratizing the flow of unmanned power where flexibility, iteration speed, and digital logistics now matter vast orders of magnitude more than static inventories or centralized mass. For India, then, the message from history is clear. By printing drones at the edge, improvising, iterating, and integrating faster than any foe, Indian forces write the next chapter of technological war, one that turns quantity, quality, and innovation into immediate battlefield reality. These mobile units are not just a technical marvel, but a strategic imperative, echoing the disruptive breakthroughs that have, time and again, won wars and changed the world. The lesson of revolutionary technology reshaping warfare is not limited to one or two conflicts. It is a global and perpetual phenomenon. Consider how cryptography cracked at Bletchley Park gave the Allies an edge in World War II, not by brute force but by intelligence dominance. The Enigma machine, once thought unbreakable, was compromised by leaps in mathematical computation and early computer engineering, transforming codebreaking into a key pillar of strategic success. In the Pacific theater, the U.S. Navy's rapid development of carrier aviation, radar, and logistics enabled mobile task forces to leapfrog thousands of miles, overrunning islands and projecting power far beyond previous constraints. Later, the advent of jet engines rendered piston fighters obsolete. Those nations quickest to transition, Britain and the U.S., retained their air superiority, while former aviation giants struggled to catch up. Fast forward to the age of cyber warfare and autonomous systems. When Israel used AI and loitering munitions to neutralize Syrian air defenses in the Bekaa Valley in 1982, the result was not just tactical victory, but a doctrinal revolution showing that interconnected, digital strike systems could annihilate conventional defenses. Similarly, the 2008 Russo-Georgian War proved how sudden superiority in electronic intelligence and tactical UAVs could alter campaign outcomes, despite Georgia's spirited resistance. The U.S. Thunder Run into Baghdad in 2003 displayed the potency of rapid, adaptive logistics and precision navigation, enabled by digital mapping, satellite comms, and ruggedized battlefield networks. The result? Armored columns pierced resistance much faster than traditional supply doctrine had predicted. The technology-driven approach, including constant in-field reconfiguration, was a primary factor in overwhelming Iraq's centralized but slow-moving forces. More recently, the Bayraktar TB2 drones, frantically manufactured and adapted in Turkey and Ukraine, have defined phases of the Syrian civil war, the Libya intervention, and the early stages of the Russia-Ukraine war. When supply lines for ammunition or electronics became tight, local 3D printing and rapid prototyping filled the gaps, producing custom parts, upgraded sensors, and even field-expedient munitions in a matter of days. Whoever adapted fastest won the tactical advantage. What emerges is one unassailable truth: technology that can be deployed, iterated, upgraded, and manufactured at the point of need, not merely shipped from central factories, has always turned defensive wars into offensive breakthroughs. The Zuppa, Divide by Zero initiative is a direct successor to this tradition, taking the field-proven advantage of rapid drone manufacture, customization, and replenishment one step further by automating and localizing the entire chain. India, the capacity to place digitally driven, AI-optimized drone factories at brigade HQs, remote bases, and naval flotillas is like handing every commander a toolkit for tactical surprise and mission-specific innovation, no longer confined by logistics or foresight failures in distant ministries. It aligns perfectly with lessons from history. Those who decentralize innovation and put it in the hands of frontline operators can leap ahead, leaving slower, centralized adversaries behind and often unable to recover. In the battles and campaigns of the coming years, we will see unmanned aerial systems, rapid field manufacturing, and modular, mission-tailored assets become as decisive as tanks at Cambrai, jets over Korea, codebreakers at Bletchley, or drones over Ukraine. And as India builds on this tradition, the prognosis is clear. The future of war will be won by those who can invent, adapt, and deploy at the speed of thought, exactly what mobile drone units now make possible on every Indian front.